Question 1. The evaluation methodology shows that a client's facility has significant potential for load shedding during peak demand periods, which could lead to substantial financial incentives through participation in a regional demand response program. However, the client is hesitant due to concerns about potential operational disruptions and the complexity of integrating new control systems. The CEA has identified that a specific type of load, while easily controllable, is critical for a niche manufacturing process that, if interrupted, could lead to significant production downtime and reputational damage, a risk the client has not fully articulated. What is the most ethically and professionally responsible course of action for the CEA? Option A. Proceed with recommending the demand response program based on the readily available financial incentives, assuming the client will manage any operational risks independently once informed of the general program benefits. Option B. Recommend that the client avoid demand response programs altogether, as the perceived complexity and potential for disruption outweigh the benefits, and instead focus solely on traditional energy efficiency upgrades that do not involve load management. Option C. Advise the client to proceed with demand response participation, focusing on the potential financial gains and downplaying the risks associated with interrupting the critical manufacturing load, while suggesting a phased implementation to mitigate some operational concerns. Option D. Conduct a detailed risk assessment of interrupting the critical manufacturing load, clearly quantifying the potential financial and operational consequences of such an interruption, and present this information transparently to the client alongside the potential demand response benefits and costs, recommending a course of action that prioritizes operational stability if the risks outweigh the incentives. The correct answer is C. Advise the client to proceed with demand response participation, focusing on the potential financial gains and downplaying the risks associated with interrupting the critical manufacturing load, while suggesting a phased implementation to mitigate some operational concerns. Explanation. This scenario presents a professional challenge for a certified energy auditor, C, due to the inherent conflict between maximizing energy savings for the client and adhering to the principles of demand response programs, which often involve broader grid stability and cost-effectiveness for all consumers. The CEA must navigate this ethical dilemma by prioritizing accurate data and transparent reporting over potentially misleading or incomplete information that might favor a specific outcome. The professional challenge lies in balancing the client's immediate financial interests with the integrity of energy management practices and the broader objectives of demand response. The correct approach involves a thorough and unbiased evaluation of the facility's load profile and its potential for participation in demand response programs. This includes accurately identifying controllable loads, assessing the technical feasibility of load shedding or shifting, and transparently communicating the potential benefits and drawbacks to the client, including any limitations or contractual obligations associated with demand response participation. This approach is ethically sound and professionally responsible because it upholds the CEA's duty to provide objective advice based on sound engineering principles and regulatory compliance. It aligns with the principles of energy efficiency and demand response as outlined in relevant U.S. regulations and industry best practices, which emphasize data integrity, transparency, and the pursuit of sustainable energy solutions that benefit both the individual facility and the wider energy system. An incorrect approach would be to selectively present data that exaggerates the benefits of demand response participation without acknowledging potential downsides or technical limitations. This could involve downplaying the costs of implementing control systems, overstating the reliability of demand response incentives, or failing to disclose any potential negative impacts on operational continuity. Such an approach would be ethically compromised as it misleads the client and undermines the credibility of the CEA. It also violates the spirit of demand response programs, which are designed for mutual benefit and grid reliability, not for creating artificial savings through incomplete reporting. Another incorrect approach would be to dismiss demand response entirely without a proper technical assessment, based on a preconceived notion or a desire to focus solely on traditional energy efficiency measures. This fails to explore all viable avenues for energy cost reduction and grid support, potentially leaving the client with suboptimal energy management strategies. The professional decision-making process for similar situations requires a commitment to data-driven analysis, ethical conduct, and clear communication. A CEA should always begin by understanding the client's objectives and then conducting a comprehensive assessment of the facility's energy usage and potential for load management. This assessment must be objective and consider all relevant technical, economic, and regulatory factors. Transparency with the client about findings, including both benefits and risks, is paramount. When faced with conflicting interests, the CEA must prioritize accuracy, integrity, and adherence to established professional standards and regulatory frameworks. Question 2. Comparative studies suggest that evacuated tube collectors offer distinct advantages in certain solar thermal applications. If a certified energy auditor, CE, is tasked with evaluating their suitability for a project where specific manufacturer performance data is unavailable, which of the following approaches best aligns with professional due diligence and ethical practice? Option A. Recommend the technology based on its popularity and successful implementation in geographically and climatically dissimilar regions. Option B. Assess the evacuated tube collector's fundamental design principles, construction materials, and known performance characteristics under varying environmental conditions to infer its suitability for the intended application. Option C. Prioritize the technology based on its potentially lower upfront purchase price, assuming performance will be adequate. Option D. Accept a peer's anecdotal endorsement of the technology without independent verification or technical analysis. The correct answer is B. Assess the evacuated tube collector's fundamental design principles, construction materials, and known performance characteristics under varying environmental conditions to infer its suitability for the intended application. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified energy auditor, CE, by requiring them to evaluate the suitability of evacuated tube collectors for a specific application without relying on direct performance data from the manufacturer. This necessitates a deep understanding of the underlying design principles, construction materials, and inherent performance characteristics of evacuated tube collectors, as well as their typical application limitations. Challenge lies in making a sound recommendation based on theoretical knowledge and general performance trends when specific, site or product-specific data is unavailable, ensuring the recommendation aligns with the principles of energy efficiency and responsible technology adoption as guided by professional standards. Correct approach analysis. The correct approach involves a thorough assessment of the evacuated tube collector's design features, such as the vacuum insulation, selective coatings, and heat pipe or direct flow mechanisms, and how these contribute to its performance characteristics, particularly its efficiency at higher temperatures and in diffuse light conditions. This approach is justified because it directly addresses the fundamental physics and engineering of the technology. By understanding these inherent characteristics, the CEA can infer its likely performance in the given application context, considering factors like ambient temperature, solar irradiance, and the required heat output temperature. This aligns with the CEA's ethical obligation to provide recommendations based on sound technical principles and a comprehensive understanding of the technology, as implicitly required by professional certification standards that emphasize competence and due diligence. It allows for a reasoned judgment even in the absence of specific manufacturer data, promoting informed decision-making. Incorrect approaches analysis, recommending the technology solely based on its widespread use in other regions, without considering the specific climatic and application conditions of the target site, represents a failure in due diligence. This approach ignores the critical impact of environmental factors on collector performance and may lead to an inefficient or unsuitable system, violating the CEA's responsibility to recommend cost-effective and appropriate solutions. Suggesting the technology based on a single, unverified testimonial from a peer without independent verification or analysis of the underlying performance principles is also professionally unsound. This relies on anecdotal evidence rather than objective technical assessment, which is contrary to the scientific and engineering basis of energy auditing, and could lead to a misinformed recommendation. Choosing the technology based on its perceived lower initial cost without a comprehensive performance evaluation is a significant ethical and professional failure. Energy auditing emphasizes life cycle cost and performance, not just upfront expenditure. Ignoring the performance characteristics and potential long-term operational inefficiencies due to a lower initial cost can result in a system that is not truly cost-effective or energy efficient, failing to meet the core objectives of an energy audit. Professional reasoning. Professionals in this situation should adopt a systematic approach. First, they must acknowledge the limitations of available data and identify the need for inferential analysis. Second, they should leverage their foundational knowledge of the technology's design and physics to predict performance under the given conditions. Third, they should consider the typical application envelopes and limitations of the technology. Finally, they should clearly communicate any assumptions made and the basis for their recommendation, highlighting areas where further specific data would enhance confidence. This structured reasoning process ensures that recommendations are technically defensible and ethically sound, even when faced with incomplete information. Question 3. Operational review demonstrates that a recently installed rooftop photovoltaic system exhibits neatly routed wiring and securely fastened mounting structures. However, there is no readily apparent documentation detailing the specific grounding and bonding methods employed for the system's components and the overall array. Considering the regulatory framework for PV system installations in the United States, which of the following approaches is the most professionally responsible and compliant for the energy auditor? Option A. Conclude that the system is safe and compliant because it is currently generating electricity without any apparent faults. Option B. Rely on the installer's verbal confirmation that all grounding and bonding requirements were met during the installation process. Option C. Verify the grounding and bonding methods against the requirements of the National Electrical Code, NEC, as adopted by the local jurisdiction, ensuring proper conductor sizing, connection points, and continuity of the grounding path for all conductive components of the PV system and associated equipment. Option D. Accept the installation as compliant based on the visual neatness of the wiring and the secure mounting of the structures, assuming the installer followed standard practices. Correct answer is C. Verify the grounding and bonding methods against the requirements of the National Electrical Code, NEC, as adopted by the local jurisdiction, ensuring proper conductor sizing, connection points, and continuity of the grounding path for all conductive components of the PV system and associated equipment. Explanation. Scenario analysis. This scenario presents a common challenge in PV system installations where multiple stakeholders, including the installer, the client, and potentially regulatory bodies, have differing interpretations of safety and installation standards. The professional challenge lies in ensuring that the installation not only meets the client's immediate needs, but also adheres strictly to the applicable safety regulations and best practices for PV systems, particularly concerning grounding and wiring. Failure to do so can lead to safety hazards, system underperformance, and legal liabilities. The auditor must exercise sound judgment to identify deviations from established standards and recommend corrective actions that prioritize safety and compliance. Correct approach analysis. The correct approach involves a thorough review of the installation against the National Electrical Code, NEC, as adopted and enforced by the relevant U.S. jurisdiction, specifically focusing on Article 690 for solar photovoltaic systems and Article 250 for grounding and bonding. This approach is correct because it directly addresses the core safety and performance requirements for PV systems. Proper grounding, as mandated by the NEC, is critical for protecting personnel and equipment from electrical shock and lightning-induced surges. The NEC specifies requirements for equipment grounding conductors, grounding electrode systems, and bonding to ensure a safe and effective path for fault currents. Furthermore, adherence to NEC wiring practices ensures that conductors are appropriately sized, protected, and installed to prevent overheating, insulation damage, and fire hazards. This systematic, code-compliant review is the bedrock of professional responsibility for an energy auditor. Incorrect approach is analysis, an approach that prioritizes only the visual appearance of the wiring and mounting structures, without verifying their compliance with grounding and bonding requirements, is incorrect. This failure stems from neglecting the fundamental safety mandates of the NEC regarding grounding. While neat wiring might be aesthetically pleasing, it does not guarantee electrical safety or system integrity. Another incorrect approach is to assume that because the system is producing power, all safety regulations have been met. This is a dangerous assumption that overlooks critical safety aspects like proper grounding and bonding, which are essential for preventing hazards even when the system is operational. The NEC's requirements for grounding are not contingent on system output, but on the inherent risks associated with electrical systems. Finally, An approach that relies solely on the installer's verbal assurances regarding compliance, without independent verification against the NEC, is professionally negligent. While installers are expected to follow codes, an auditor's role is to provide an objective assessment. Verbal assurances do not substitute for documented compliance with established safety standards. This approach fails to uphold the auditor's duty to ensure the installation meets all regulatory requirements. Professional reasoning. Professionals in this field must adopt a systematic, code-driven approach. The decision-making process should begin with identifying the applicable regulatory framework, in this case, the NEC as enforced in the relevant U.S. jurisdiction. Next, the auditor should develop a checklist based on the NEC requirements for PV system installation, covering mounting structures, wiring practices, grounding, and safety. During the review, each aspect of the installation should be compared against these code requirements. Any discrepancies should be documented, and corrective actions recommended that bring the installation into full compliance. This process ensures that safety and regulatory adherence are paramount, protecting both individuals and the integrity of the PV system. Question 4. Regulatory review indicates that a proposed wind energy project's economic viability is heavily influenced by a combination of federal tax credits and state-level renewable energy certificate (REC) markets. As a certified energy auditor, which approach best reflects a comprehensive and compliant assessment of the project's wind energy economics, considering the impact of these incentives on its levelized cost of energy, (LCO). Option A. Develop a detailed financial model that projects all capital and operational expenditures, estimates potential revenue from electricity sales and REC generation, and quantifies the impact of both current and potential future federal tax credits and REC market fluctuations on the project's LCO. Option B. Determine the LCO by subtracting the value of the federal tax credits from the total projected capital costs, and then dividing by the estimated total energy production, disregarding the ongoing operational costs and the REC market. Option C. Focus primarily on the technical specifications of the wind turbines and their expected energy output, using this data to estimate the LCO without a detailed analysis of the specific incentive structures or their long-term stability. Option D. Calculate the LCO based solely on the projected operational costs and the current market value of RECs, assuming the federal tax credits will remain constant and fully utilized throughout the project's lifespan. The correct answer is D. Calculate the LCO based solely on the projected operational costs and the current market value of RECs, assuming the federal tax credits will remain constant and fully utilized throughout the project's lifespan. Explanation. Scenario analysis. This scenario presents a common challenge for energy auditors, balancing the technical feasibility of a renewable energy project with its economic viability and the complex landscape of regulatory incentives. The professional challenge lies in accurately assessing the long-term financial implications of a wind energy project, considering not just upfront capital costs, but also operational expenses, potential revenue streams, and the impact of evolving incentive structures. Misinterpreting or misapplying these economic and regulatory factors can lead to flawed recommendations, potentially resulting in significant financial losses for the client and damage to the auditor's professional reputation. The auditor must demonstrate a deep understanding of wind energy economics and the specific regulatory framework governing incentives to provide sound advice. Correct approach analysis. The correct approach involves a comprehensive analysis that integrates the projected operational costs and revenue streams of the wind farm with the current and anticipated regulatory incentives. This includes a thorough understanding of how different incentive mechanisms, e.g., tax credits, renewable energy certificates, production incentives, are structured, their duration, and their impact on the project's overall profitability and the levelized cost of energy, LCO. The auditor must critically evaluate the stability and longevity of these incentives, considering potential policy changes. This approach aligns with professional ethical obligations to provide accurate, objective, and client-focused advice, ensuring that recommendations are grounded in a realistic assessment of financial performance and regulatory support. It directly addresses the core competencies of a certified energy auditor in evaluating the economic feasibility of energy projects. Incorrect approach is analysis, focusing solely on the initial capital expenditure and ignoring operational costs and revenue projections, is a significant failure. This approach provides an incomplete picture of the project's true economic performance and fails to account for the ongoing expenses and income that are critical to long-term viability. It also neglects the crucial role of incentives in shaping the project's financial attractiveness. Prioritizing only the most lucrative current incentives without considering their potential expiration or modification is another flawed strategy. Regulatory incentives are subject to change, and basing an entire economic assessment on a snapshot of current benefits without accounting for future uncertainty can lead to overestimation of profitability and unrealistic ELCO figures. This demonstrates a lack of foresight and a failure to conduct a robust risk assessment. Overemphasizing the technical efficiency of the wind turbines without a corresponding rigorous economic analysis is also problematic. While technical performance is important, it does not guarantee economic success. An auditor must connect technical capabilities to financial outcomes, considering how efficiency translates into revenue and impacts operational costs, and how this interacts with the incentive landscape. This approach neglects the fundamental economic principles required for sound investment decisions. Professional reasoning. Professionals should adopt a holistic approach that integrates technical assessment with a comprehensive economic and regulatory analysis. This involves 1. Understanding the client's financial objectives and risk tolerance. 2. Conducting a detailed cost-benefit analysis that includes all capital and operational expenditures, as well as projected revenue streams. 3. Thoroughly researching and understanding all applicable federal, state, and local incentives, including their terms, conditions, and potential for change. 4. Calculating and analyzing the ELCO, considering the impact of incentives on this metric. 5. Performing sensitivity analysis to understand how changes in key variables, e.g., energy prices, incentive levels, operational costs, might affect project profitability. 6. Clearly communicating the assumptions, risks, and uncertainties associated with the economic projections to the client. Question 5. Consider a scenario where a certified energy auditor, CEA, is tasked with evaluating a potential site for a new wind farm. The site has a history of moderate average wind speeds. The CEA is preparing a preliminary report for investors. Which of the following approaches to assessing the site's wind characteristics would best demonstrate professional due diligence and adherence to regulatory expectations for a renewable energy project? Option A. Using a simplified wind power density calculation based on limited, non-site-specific data to quickly estimate the energy output without further investigation into turbulence or shear. Option B. Conducting a detailed risk assessment that quantifies the potential impact of wind speed variability, directional changes, turbulence intensity, wind shear, and wind power density on projected energy production and turbine operational life. Option C. Focusing primarily on the prevailing wind direction, as this is the most critical factor for turbine placement and energy capture, while giving minimal attention to other wind characteristics. Option D. Relying solely on historical meteorological data to establish an average wind speed, assuming this single metric is sufficient for determining the site's energy potential. The correct answer is B. Conducting a detailed risk assessment that quantifies the potential impact of wind speed variability, directional changes, turbulence intensity, wind shear, and wind power density on projected energy production and turbine operational life. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified energy auditor, CEA, due to the inherent variability and complexity of wind characteristics. Accurately assessing these characteristics is crucial for determining the viability and optimal design of a wind energy project. The challenge lies in moving beyond a superficial understanding to a risk-informed approach that considers the potential consequences of misinterpreting or underestimating these factors. CEA must demonstrate due diligence in evaluating the site's wind resource, recognizing that inaccurate assessments can lead to significant financial losses, underperformance of the wind farm, and potential environmental impacts if the project is ultimately unsuccessful or inefficient. The professional responsibility extends to ensuring that the assessment is robust enough to support sound investment and engineering decisions. Correct approach analysis. The correct approach involves a comprehensive risk assessment that explicitly considers the implications of wind speed variability, directional patterns, turbulence intensity, wind shear, and wind power density on the proposed wind energy project's performance and economic viability. This approach is right because it aligns with the professional standards expected of a CEA, which mandate a thorough and evidence-based evaluation. Specifically, regulatory frameworks and professional guidelines for energy auditing, particularly those with a renewable energy focus, emphasize the importance of identifying and quantifying risks associated with resource assessment. A risk assessment framework allows the CEA to systematically evaluate how deviations from expected wind characteristics could impact energy production, structural integrity of turbines, and overall project profitability. This proactive identification of potential issues enables the development of mitigation strategies and more realistic project projections, fulfilling the ethical obligation to provide accurate and reliable information to stakeholders. Incorrect approaches analysis, an approach that focuses solely on average wind speed without considering its variability or the impact of turbulence, would be professionally unacceptable. This failure stems from neglecting critical aspects of wind resource assessment that directly influence turbine performance and lifespan. Regulatory guidelines require a holistic view, and ignoring turbulence, for instance, can lead to premature wear on turbine components and reduced energy capture, representing a significant financial and operational risk that has not been adequately assessed. Another incorrect approach would be to prioritize only wind direction without a detailed analysis of wind shear. Wind shear, the change in wind speed with height, is a fundamental factor in turbine power output and structural loading. Failing to account for it can lead to an overestimation of energy production at hub height and an underestimation of the stresses on the turbine tower and blades, violating the CEA's duty to provide a comprehensive and technically sound evaluation. Finally, an approach that overlooks the wind power density in favor of simpler metrics would also be flawed. Wind power density is a direct indicator of the energy potential of a site. Without this crucial metric, the CEA cannot accurately compare different sites or turbine technologies, nor can they provide a robust basis for financial modeling. This omission represents a failure to apply standard industry practices and a lack of due diligence in resource assessment, potentially leading to the selection of an uneconomical or underperforming site. Professional reasoning. Professionals in this field should adopt a systematic risk assessment methodology. This involves 1. Identifying all relevant wind characteristics: speed, direction, turbulence, shear, power density, and their potential impact on the project. 2. Gathering site-specific data through reliable measurement campaigns or validated modeling. 3. Quantifying the uncertainty and potential variability associated with each characteristic. 4. Evaluating the consequences of these uncertainties on project performance, economics, and safety. 5. Developing mitigation strategies or recommending appropriate turbine selection and operational parameters based on the risk assessment. This structured approach ensures that all critical factors are considered, leading to more informed and defensible recommendations. Question 6. Market research demonstrates a growing interest in small-scale hydropower projects in a specific U.S. region. As a certified energy auditor, you are tasked with assessing the hydropower resource potential for a proposed site. You have access to historical rainfall data for the general area, but limited information on the specific stream flow and detailed topography of the project site. Which of the following approaches would best ensure a robust and compliant hydropower resource assessment according to U.S. regulatory frameworks for renewable energy projects? Option A. Utilize a generic hydrological model that has been widely used for similar projects in other regions, assuming its applicability to the current site. Option B. Prioritize obtaining accurate, site-specific stream flow measurements and conducting a detailed topographic survey of the project area to inform the selection and calibration of an appropriate hydrological model. Option C. Rely primarily on historical rainfall data for the region, using it to estimate stream flow through generalized regional hydrological models. Option D. Conduct a comprehensive topographic survey of the project site and use this data to estimate potential power output, deferring detailed stream flow analysis to a later stage. The correct answer is B. Prioritize obtaining accurate, site-specific stream flow measurements and conducting a detailed topographic survey of the project area to inform the selection and calibration of an appropriate hydrological model. Explanation. Scenario analysis. This scenario presents a common challenge for energy auditors: selecting the most appropriate method for assessing a critical resource, hydropower flow, under potentially varying site conditions and data availability. The professional challenge lies in balancing accuracy, cost-effectiveness, and adherence to regulatory requirements for data collection and modeling in a renewable energy project context. The auditor must exercise sound professional judgment to ensure the assessment is robust enough to support investment decisions and meet regulatory scrutiny without incurring unnecessary expenses or delays. The focus on flow measurement, topographic surveys, and hydrological modeling highlights the interdisciplinary nature of hydropower assessment and the need for a comprehensive understanding of each component's role and limitations. Correct approach analysis. The correct approach involves a phased methodology that begins with understanding the site's specific characteristics and available data, then selecting appropriate flow measurement techniques, followed by a topographic survey to define the physical constraints, and finally employing a hydrological model calibrated with the collected data. This systematic process ensures that the assessment is grounded in empirical evidence and site-specific topography, leading to a more reliable hydrological model. Regulatory frameworks for renewable energy projects, such as those overseen by the U.S. Environmental Protection Agency, EPA, or relevant state energy commissions, often mandate data-driven assessments and the use of scientifically sound modeling practices. A phased approach, starting with data acquisition and progressing to modeling, aligns with these requirements by ensuring that the model is built upon accurate and relevant inputs, thereby increasing its credibility and the reliability of the hydropower resource assessment. This also supports the principles of due diligence and responsible project development. Incorrect approaches analysis, relying solely on historical rainfall data without direct flow measurements or site-specific topographic information, is an insufficient approach. While historical data can provide context, it does not account for local hydrological variations, watershed characteristics, or the impact of existing infrastructure, all of which are critical for accurate flow assessment. This approach risks generating a model that is not representative of the actual site conditions, potentially leading to misinformed investment decisions and non-compliance with regulatory requirements for site-specific assessments. Using only a generic hydrological model without site-specific flow measurements or topographic surveys is also problematic. Generic models are based on broad assumptions and may not accurately reflect the unique geomorphology, soil types, or vegetation cover of the specific project site. Without site-specific data to calibrate and validate the model, its predictive capabilities are severely limited, and the resulting resource assessment would lack the necessary rigor for regulatory approval or financial commitment. This failure to tailor the assessment to the specific site constitutes a significant professional and regulatory lapse. Conducting a topographic survey without concurrent or subsequent flow measurements and hydrological modeling would result in an incomplete resource assessment. While topography is crucial for understanding potential dam sites, penstock routes, and power generation potential, it does not provide information on the actual water availability or its variability over time. This isolated data point, while valuable in isolation, does not fulfill the comprehensive requirements of a hydropower resource assessment, which necessitates understanding both the physical potential and the water resource itself. Professional reasoning. Professionals should adopt a decision-making framework that prioritizes data integrity and regulatory compliance. This involves 1. Understanding the regulatory landscape. Identify all applicable federal, state, and local regulations governing renewable energy project assessments, including data collection and modeling standards. 2. Site characterization. Conduct an initial assessment of the site to understand its unique hydrological and topographical features and identify potential data gaps. 3. Data acquisition strategy. Develop a plan for collecting accurate and relevant data, including appropriate flow measurement techniques and topographic survey methods, considering cost-effectiveness and project timelines. 4. Model selection and calibration. Choose a hydrological model suitable for the site's characteristics and calibrate it using the collected site-specific data. 5. Validation and reporting. Validate the model's performance and present the findings in a clear, concise report that addresses all regulatory requirements and supports informed decision-making. This structured approach ensures that all critical aspects of the hydropower resource assessment are addressed systematically, leading to a reliable and compliant outcome. Question 7. The investigation demonstrates that a proposed concentrating solar power (CSP) project utilizing a solar power tower design is being considered for a remote desert location. The primary concern raised by stakeholders is the potential for significant operational disruptions due to dust storms, which are frequent in the region. Which of the following approaches best addresses the associated risks from a certified energy auditor's perspective? Adhering to U.S. regulatory frameworks and professional standards for energy auditing. Option A. Conduct a detailed analysis of the thermodynamic cycle's theoretical efficiency and the projected energy output under ideal solar conditions, assuming dust storms are a minor, infrequent inconvenience. Option B. Form a comprehensive risk assessment that evaluates the impact of dust storms on heliostat reflectivity, receiver performance, and cooling systems, and proposes mitigation strategies such as automated cleaning systems and operational adjustments. Option C. Recommend immediate project approval based on the general benefits of solar energy, deferring any detailed assessment of operational risks to the project's construction and operational phases. Option D. Focus exclusively on the initial capital cost of the solar power tower technology, comparing it to other renewable energy options without in-depth consideration of site-specific operational challenges like dust storms. The correct answer is A. Conduct a detailed analysis of the thermodynamic cycle's theoretical efficiency and the projected energy output under ideal solar conditions, assuming dust storms are a minor, infrequent inconvenience. Explanation. The investigation demonstrates a scenario where a certified energy auditor, C, must assess the risk associated with a proposed concentrating solar power, CSP project. This is professionally challenging because CSP technologies, while promising for renewable energy generation, involve complex thermodynamic cycles and site-specific environmental factors that can introduce unique risks. The auditor must balance the potential benefits of renewable energy with the practical challenges of implementation, operational reliability, and long-term sustainability, all within the framework of relevant U.S. regulations and industry best practices for energy auditing. The correct approach involves a comprehensive risk assessment that systematically identifies potential hazards and vulnerabilities across all phases of the CSP project, from design and construction to operation and decommissioning. This includes evaluating the thermodynamic cycle's efficiency under varying solar irradiance, the structural integrity of parabolic troughs, or solar power towers against wind loads, the reliability of dish Stirling systems in diverse climatic conditions, and the potential environmental impacts. This approach aligns with the CEA's ethical obligation to provide objective and thorough assessments that protect client interests and promote responsible energy development, as guided by professional standards that emphasize due diligence and risk mitigation. An incorrect approach that focuses solely on the theoretical thermodynamic efficiency of the CSP system without considering site-specific environmental factors or operational risks would be professionally deficient. This failure stems from an incomplete risk assessment, neglecting crucial variables that directly impact project viability and safety. Such an approach could lead to underestimation of operational costs, unexpected downtime, and potential environmental noncompliance, violating the CEA's duty to provide a holistic and practical evaluation. Another incorrect approach that prioritizes the initial capital cost savings of a particular CSP technology over its long-term operational risks and maintenance requirements would also be unacceptable. This oversight represents a failure to conduct a thorough life cycle cost analysis and risk assessment, potentially leading to a project that is financially unsustainable in the long run. This contravenes the CEA's responsibility to advise clients on the most prudent and effective energy solutions, considering all relevant economic and operational factors. A third incorrect approach that overlooks potential grid integration challenges or the need for energy storage solutions, focusing only on the direct solar to electricity conversion, would be a significant professional failing. This demonstrates a lack of understanding of the broader energy system context and the practicalities of delivering reliable power. Such an approach neglects critical risks related to intermittency and grid stability, which are essential considerations for any renewable energy project. Professionals should adopt a structured risk assessment framework that begins with a clear scope definition, followed by hazard identification, risk analysis, likelihood and consequence, risk evaluation, and the development of risk treatment strategies. This systematic process ensures that all relevant factors are considered, leading to informed decision-making and the identification of appropriate mitigation measures, thereby upholding professional standards and regulatory compliance. Question 8. The analysis reveals that a wind resource assessment for a proposed utility-scale wind farm is nearing completion. The auditor is reviewing the risk management strategy employed during the assessment. Which of the following approaches to managing risks associated with the wind resource assessment best aligns with the professional standards and regulatory expectations for a certified energy auditor? Option A. Ignoring potential impacts of extreme weather events and complex terrain, concentrating solely on average wind conditions. Option B. Systematically identifying, evaluating, and mitigating risks to the accuracy and reliability of the wind resource assessment data and projections. Option C. Focusing exclusively on achieving the highest possible projected wind speeds to maximize the perceived project potential. Option D. Minimizing assessment costs by using the least expensive data collection methods and the smallest available dataset. The correct answer is B. Systematically identifying, evaluating, and mitigating risks to the accuracy and reliability of the wind resource assessment data and projections. Explanation. Scenario analysis. This scenario is professionally challenging because wind resource assessment is foundational to the economic viability and technical feasibility of a renewable energy project. Inaccurate assessment, driven by flawed risk management, can lead to significant financial losses, regulatory noncompliance, and reputational damage. The auditor must balance the need for thoroughness with practical constraints, ensuring that the chosen risk assessment approach aligns with established industry standards and regulatory expectations for energy projects. Correct approach analysis. The correct approach involves systematically identifying potential risks to the accuracy and reliability of the wind resource assessment data, evaluating their likelihood and impact, and then developing mitigation strategies. This aligns with the principles of due diligence expected of a certified energy auditor. Regulatory frameworks, such as those guiding energy project development and investment, implicitly or explicitly require a robust risk management process. This ensures that decisions are based on a realistic understanding of uncertainties and potential deviations from expected performance, thereby safeguarding stakeholder interests and promoting sustainable energy development. Incorrect approaches analysis. An approach that solely focuses on the most optimistic wind speed projections without considering potential underperformance or data anomalies fails to acknowledge inherent uncertainties. This is a regulatory failure because it deviates from the principle of providing a balanced and realistic assessment, which is crucial for informed decision-making by investors and regulators. Ethically, it misrepresents the project's potential. An approach that prioritizes minimizing assessment costs by using limited, low-quality data, even if it appears sufficient at first glance, is also problematic. This is a regulatory failure, as it likely violates standards for data collection and validation required for energy project certification. It also represents an ethical failure by compromising the integrity of the assessment for financial expediency, potentially leading to an overestimation of energy yield. An approach that ignores the potential impact of extreme weather events or site-specific topographical challenges on turbine performance, focusing only on average wind conditions, is a significant risk. This is a regulatory failure because it neglects critical factors that can affect long-term energy production and operational safety, which are often stipulated in environmental and operational guidelines for renewable energy installations. It also demonstrates a lack of professional diligence in understanding the full spectrum of operational risks. Professional reasoning. Professionals should adopt a structured risk management framework. This involves 1. Clearly defining the scope and objectives of the wind resource assessment. 2. Identifying all potential risks, including data quality, measurement errors, meteorological variability, and site-specific factors. 3. Qualitatively and quantitatively assessing the likelihood and impact of each identified risk. 4. Developing and documenting specific mitigation strategies for high-priority risks. And 5. Regularly reviewing and updating the risk assessment throughout the project lifecycle. This systematic process ensures that the assessment is robust, defensible, and compliant with professional and regulatory expectations. Question 9. Operational review demonstrates that a proposed photovoltaic PV system installation site exhibits significant potential for solar energy generation. The site's geographical location and orientation are favorable, but preliminary site assessments have generated sun path diagrams and shading analysis reports. As a certified energy auditor, C, operating under U.S. regulatory frameworks, how should you conceptually interpret these diagrams and reports to inform your assessment of the PV system's potential without performing detailed irradiance calculations? Option A. Focus exclusively on the theoretical solar constant and air mass values to determine the average solar radiation reaching the site, considering these as the primary determinants of PV system performance. Option B. Disregard the sun path diagrams and shading analysis reports as they do not provide precise solar irradiance values, and instead rely solely on the theoretical solar constant to estimate the maximum possible solar energy incident on the site. Option C. Utilize the sun path diagrams to understand the sun's trajectory across the sky throughout the year, and the shading analysis reports to identify specific times and durations when obstructions will block direct sunlight from reaching the proposed PV array locations, thereby qualitatively assessing the impact on solar resource availability. Option D. Assume that any identified shading on the sun path diagram indicates a complete failure of the PV system's viability, and recommend against installation without further investigation. Correct answer is C. Utilize the sun path diagrams to understand the sun's trajectory across the sky throughout the year, and the shading analysis reports to identify specific times and durations when obstructions will block direct sunlight from reaching the proposed PV array locations, thereby qualitatively assessing the impact on solar resource availability. Explanation. This scenario presents a professional challenge because it requires an energy auditor to interpret complex solar geometry and its impact on renewable energy system performance without relying on precise mathematical calculations, which are often the primary tools for such analysis. The auditor must demonstrate a conceptual understanding of how solar angles and atmospheric conditions influence the amount of solar radiation reaching a photovoltaic PV array, and how these factors are represented in tools like sun path diagrams and shading analysis reports. The professional challenge lies in translating theoretical knowledge into practical assessment of system viability and performance expectations, adhering to the specific regulatory framework governing energy audits in the United States, as implied by the CEA certification context. The correct approach involves utilizing sun path diagrams and shading analysis reports to qualitatively assess the potential for solar resource availability and identify significant obstructions. This method is correct because it aligns with the practical application of solar energy principles as understood within the U.S. regulatory context for energy efficiency and renewable energy assessments. Sun path diagrams provide a visual representation of the sun's movement throughout the day and year, allowing for an understanding of potential solar exposure at different times. Shading analysis reports, when interpreted conceptually, highlight areas where obstructions, buildings, trees, etc., will reduce the direct solar radiation reaching the PV panels. This qualitative assessment is crucial for initial feasibility studies and for communicating potential performance limitations to stakeholders without needing to perform detailed irradiance calculations. This aligns with the CEA's role in providing actionable insights based on established energy assessment principles. An incorrect approach would be to dismiss the importance of sun path diagrams and shading analysis because precise irradiance values are not immediately available. This fails to acknowledge the fundamental role of these tools in understanding solar resource potential and identifying critical performance detractors. Ethically, an auditor has a responsibility to conduct a thorough assessment, and ignoring readily available visual aids that inform solar resource availability is a dereliction of that duty. This approach also fails to meet the implicit regulatory expectation of understanding the site-specific solar conditions that influence renewable energy system performance. Another incorrect approach would be to solely focus on the theoretical solar constant without considering atmospheric effects or site-specific obstructions. While the solar constant is a fundamental value, it represents radiation outside Earth's atmosphere. Its direct application without accounting for air mass, which modifies the radiation reaching the surface and local shading, would lead to an inaccurate and overly optimistic assessment of available solar energy. This is professionally unsound, as it provides a misleading picture of the actual energy potential, potentially leading to poor investment decisions by the client. It also fails to adhere to the practical requirements of site-specific energy auditing, which necessitates considering real-world conditions. A third incorrect approach would be to assume that any shading identified on a sun path diagram will render a PV system unviable without further qualitative assessment. This demonstrates a lack of nuanced understanding. Shading analysis is intended to identify significant shading that materially impacts performance. Minor, intermittent shading might be acceptable or manageable with specific PV technologies, e.g., microinverters. An overly simplistic binary interpretation of shading data is professionally deficient and fails to provide the client with a balanced perspective on the system's potential. It also overlooks the analytical skill required to interpret these tools effectively. The professional decision-making process for similar situations should involve first understanding the purpose of the tools provided, sun path diagrams, shading analysis reports, within the context of solar energy assessment. This means recognizing their role in visualizing solar geometry and identifying potential obstructions. The auditor should then qualitatively interpret this information, considering how the sun's path interacts with the site's topography and surrounding structures. The next step is to communicate these findings clearly to the client, highlighting potential benefits and limitations of a solar installation based on the observed solar resource and shading conditions. If specific irradiance data is required for detailed financial modeling, the auditor should clearly state this need and recommend further specialized analysis, rather than attempting to derive precise values from qualitative tools. This approach ensures a thorough, ethical, and professionally responsible assessment that meets regulatory expectations for energy audits. Question 10. To address the challenge of selecting the most appropriate turbine type for a new small-scale hydropower project on a river with highly variable flow and a moderate fluctuating head, which approach best aligns with the certified energy auditor (C) responsibilities under U.S. regulatory frameworks, focusing on long-term operational effectiveness and environmental compliance. Option A. Prioritize the turbine type with the highest peak efficiency rating, assuming it will deliver the most energy regardless of specific site conditions. Option B. Select the turbine type with the lowest upfront installation cost to maximize immediate project affordability, deferring detailed efficiency and environmental impact analysis to a later stage. Option C. Conduct a detailed site assessment of the river's hydraulic characteristics, head and flow, and evaluate potential turbine types, Pelton, Francis, Kaplan, against these conditions, alongside a thorough review of relevant U.S. federal and state environmental regulations and permitting requirements. Option D. Choose a turbine based on its historical prevalence in similar geographical regions, without a specific analysis of the current project's unique hydraulic and regulatory landscape. The correct answer is A. Prioritize the turbine type with the highest peak efficiency rating, assuming it will deliver the most energy regardless of specific site conditions. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified energy auditor, (C), due to the critical need to align turbine selection with specific site conditions and regulatory compliance, particularly concerning environmental impact and operational efficiency. The CEA must balance technical feasibility, economic viability, and adherence to the governing regulatory framework, which in this context is assumed to be U.S. federal and state regulations pertaining to hydropower development and environmental stewardship. Misjudging the turbine type can lead to suboptimal energy generation, increased operational costs, environmental damage, and potential noncompliance with permits and standards, all of which carry significant professional and financial repercussions. Correct approach analysis. The correct approach involves a comprehensive site assessment that prioritizes the specific head and flow characteristics of the river, alongside an evaluation of environmental sensitivities and regulatory requirements. This approach is justified by the fundamental principles of turbine selection, where Pelton turbines are best suited for high head, low flow conditions, Francis turbines for medium head and medium flow, and Kaplan turbines for low head, high flow conditions. Adhering to the U.S. regulatory framework, such as the Federal Power Act and state-level environmental impact assessments, mandates that the chosen turbine must minimize ecological disruption, e.g., fish passage, sediment transport, and maximize energy capture within the site's hydraulic constraints. This ensures both operational efficiency and compliance with environmental protection laws and permits. Incorrect approaches analysis. An approach that solely focuses on the highest theoretical efficiency rating without considering the site's specific head and flow is professionally unacceptable. This ignores the fundamental operational envelopes of different turbine types and would likely lead to a turbine that performs poorly or not at all under the actual site conditions, violating the CEA's duty to provide technically sound recommendations. Another incorrect approach would be to select a turbine based on the lowest initial capital cost, without a thorough analysis of long-term operational efficiency and maintenance requirements. This fails to meet the CEA's responsibility to recommend solutions that are economically sustainable and provide the best value over the project's life cycle, potentially violating cost-benefit analysis requirements mandated by funding or regulatory bodies. Furthermore, an approach that disregards environmental impact assessments and regulatory permitting requirements, such as those outlined by the Environmental Protection Agency, EPA, or the Army Corps of Engineers, is a direct violation of legal and ethical obligations. This could lead to significant project delays, fines, and reputational damage, undermining the credibility of the CEA and the project itself. Professional reasoning. Professionals in this situation should employ a systematic decision-making process that begins with a thorough understanding of the site's hydraulic parameters, head and flow variability. This is followed by an in-depth review of all applicable U.S. federal and state regulations, including environmental impact studies, permitting processes, and energy production standards. The CEA must then evaluate each turbine type against these site-specific and regulatory criteria, considering not only peak efficiency, but also operational range, reliability, maintenance, and environmental compatibility. The final recommendation should be a well-documented justification that clearly articulates how the chosen turbine best meets all technical, economic, and regulatory requirements, ensuring responsible and effective energy development. Question 11. The review process indicates that a hydropower facility's operational records for its penstock, intake, powerhouse, generator, and control systems are being assessed for compliance with applicable U.S. federal and state regulations. Which of the following actions by the certified energy auditor best ensures regulatory adherence and professional responsibility? Option A. Conducting a visual inspection of the powerhouse and generator only, as these are the most visible components. Option B. Confirming that the generator and control systems are operating at peak efficiency, as this is the primary focus of energy audits. Option C. Verifying that the facility's maintenance logs and inspection reports for all critical components align with the requirements stipulated by the Federal Energy Regulatory Commission, FERC, and relevant state dam safety regulations. Option D. Relying on the facility's self-reported compliance status, assuming their internal procedures are adequate. The correct answer is C. Verifying that the facility's maintenance logs and inspection reports for all critical components align with the requirements stipulated by the Federal Energy Regulatory Commission, FERC, and relevant state dam safety regulations. Explanation. The review process indicates a potential compliance gap in the operational procedures for a hydropower facility, specifically concerning the maintenance and inspection of critical components. This scenario is professionally challenging because it requires the certified energy auditor, C, to not only understand the technical function of hydropower components, but also to interpret and apply relevant regulatory frameworks to ensure safety, efficiency, and environmental protection. The CEA must exercise careful judgment to identify deviations from established standards and recommend corrective actions that align with regulatory mandates. The correct approach involves a thorough examination of the facility's maintenance logs and inspection reports for the penstock, intake, powerhouse, generator, and control systems, cross-referencing them against the requirements outlined in the relevant U.S. federal and state regulations governing hydropower operations and dam safety. This includes, but is not limited to, guidelines from the Federal Energy Regulatory Commission, FERC, for licensed projects and potentially state-specific dam safety regulations. The justification for this approach lies in its direct adherence to regulatory compliance, which is paramount for ensuring the safe and reliable operation of the hydropower plant. By verifying that maintenance and inspection activities meet or exceed regulatory standards, the CEA upholds professional ethics by prioritizing public safety and environmental stewardship, as mandated by law. An incorrect approach would be to rely solely on the facility's internal operational guidelines, without verifying their alignment with external regulatory requirements. This is professionally unacceptable because internal guidelines may not be sufficiently stringent or may not address all aspects mandated by law, leading to potential safety hazards or environmental noncompliance. Another incorrect approach would be to focus exclusively on the efficiency of the generator and control systems, while neglecting the structural integrity and operational readiness of the penstock and intake. This is a regulatory failure because regulations often place significant emphasis on the physical integrity of the dam and its associated structures to prevent catastrophic failures, irrespective of the efficiency of downstream components. A third incorrect approach would be to assume that because the facility has been operating without incident, all components are compliant. This is a flawed assumption and a professional oversight, as regulatory compliance is an ongoing requirement, not a state achieved through passive operation. Incidents can occur due to latent issues that only become apparent during rigorous inspection and maintenance, as dictated by regulatory frameworks. Professional decision-making in similar situations requires a systematic approach. First, identify the specific regulatory jurisdiction and relevant standards applicable to the facility. Second, develop a comprehensive audit plan that covers all critical components and operational aspects, ensuring it aligns with regulatory mandates. Third, meticulously gather and analyze evidence, such as maintenance records, inspection reports, and operational data. Fourth, critically evaluate the evidence against the established regulatory requirements, identifying any discrepancies or potential noncompliance. Finally, communicate findings clearly and provide actionable recommendations for corrective measures, prioritizing those that address regulatory noncompliance and potential safety or environmental risks. Question 12. What factors determine the specific permitting requirements, environmental mitigation strategies, and grid integration standards that a proposed utility-scale wind energy project must adhere to within the United States for a certified energy auditor? Option A. The project developer's preferred timeline for construction and the estimated levelized cost of energy, assuming that regulatory compliance can be addressed as a secondary concern. Option B. The specific federal, state, and local laws and regulations governing land use, environmental protection, aviation safety, and electricity transmission infrastructure, as well as the interconnection guidelines of the relevant regional transmission organization or independent system operator. Option C. The recommendations of the wind turbine manufacturer and the project's internal engineering team, as these entities are assumed to possess comprehensive knowledge of all applicable regulatory obligations. Option D. The prevailing market price for wind energy credits and the availability of federal tax incentives, with the understanding that environmental and grid integration requirements are generally standardized across all projects. The correct answer is B. The specific federal, state, and local laws and regulations governing land use, environmental protection, aviation safety, and electricity transmission infrastructure, as well as the interconnection guidelines of the relevant regional transmission organization or independent system operator. Explanation. This scenario presents a professional challenge for a certified energy auditor, C, tasked with evaluating a proposed wind energy project. The challenge lies in navigating the complex interplay of permitting processes, environmental regulations, and grid integration standards, all of which are subject to specific jurisdictional requirements. A CEA must not only understand the technical aspects of wind energy, but also possess a thorough grasp of the legal and regulatory landscape to ensure compliance and facilitate project viability. The need for careful judgment arises from the potential for conflicting requirements, the dynamic nature of regulations, and the significant financial and environmental implications of a project. The correct approach involves a comprehensive review of all applicable federal, state, and local regulations pertaining to wind energy development. This includes identifying all necessary permits, e.g., environmental impact assessments, land use permits, aviation clearance, understanding the specific environmental mitigation measures required by agencies like the U.S. Fish and Wildlife Service or state environmental protection departments, and verifying compliance with grid interconnection standards set by entities such as the North American Electric Reliability Corporation, NERC, or regional transmission organizations, RTO. This approach is correct because it directly addresses the regulatory framework mandated for CEA practice in the United States, ensuring that the project meets all legal obligations and operational requirements. It prioritizes a systematic and thorough due diligence process, which is ethically sound and professionally responsible. An incorrect approach would be to focus solely on the technical feasibility and economic projections of the wind farm, neglecting the permitting and environmental review processes. This fails to acknowledge the legal prerequisites for project construction and operation, potentially leading to significant delays, fines, or outright project cancellation. Such an approach violates the CEA's professional responsibility to ensure projects comply with all relevant laws and regulations. Another incorrect approach would be to assume that compliance with one set of regulations, e.g., federal environmental laws, automatically satisfies all other requirements, such as local zoning ordinances or grid interconnection protocols. This oversight ignores the layered nature of regulatory authority and the specific mandates of different governing bodies. It demonstrates a lack of comprehensive understanding of the regulatory environment and a failure to perform adequate due diligence, which is a significant ethical and professional failing. Finally, an approach that prioritizes expediency by seeking to bypass or minimize certain regulatory hurdles, even if seemingly minor, is also incorrect. This demonstrates a disregard for the legal and environmental protections established by regulatory bodies and can lead to severe legal repercussions and reputational damage. The professional decision-making process for similar situations should involve a structured approach. First, identify all relevant jurisdictions and governing bodies. Second, meticulously research and document all applicable regulations, permits, and standards. Third, consult with legal counsel and regulatory experts when uncertainties arise. Fourth, integrate this regulatory understanding into the project's technical and economic evaluation. And fifth, clearly communicate any identified regulatory challenges and their potential impacts to stakeholders. This systematic process ensures that all critical factors are considered, leading to informed and compliant project assessments. Question 13. Governance review demonstrates that a client is highly enthusiastic about installing vertical axis wind turbines, VAWT, for their facility, specifically mentioning their interest in Darius designs due to their perceived aesthetic appeal and potential for high wind capture. As a certified energy auditor, CEA, operating under U.S. regulatory frameworks, what is the most professionally responsible and ethically sound approach to addressing this client's request? Option A. Focus the recommendation solely on the theoretical benefits of VAWT, such as their omnidirectional wind capture, without delving into potential disadvantages or site-specific limitations, to maintain client enthusiasm. Option B. Advise the client that VAWT are generally unsuitable for most commercial applications in the U.S. and steer them towards more conventional renewable energy options without a thorough site-specific evaluation of VAWT potential. Option C. Conduct a detailed site-specific assessment to evaluate the technical feasibility, economic viability, and environmental impact of various VAWT types, including Darius and Savonius, and compare them against other suitable renewable energy technologies and energy efficiency measures, presenting an objective recommendation based on data. Option D. Recommend a specific Darius VAWT model immediately, highlighting its aesthetic advantages and theoretical wind capture capabilities, to satisfy the client's expressed preference and expedite the project. The correct answer is C. Conduct a detailed site-specific assessment to evaluate the technical feasibility, economic viability, and environmental impact of various VAWT types, including Darius and Savonius, and compare them against other suitable renewable energy technologies and energy efficiency measures, presenting an objective recommendation based on data. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified energy auditor, CEA, where a client is advocating for a specific renewable energy technology, vertical axis wind turbines, VAWT, without a thorough, objective assessment of its suitability. The CEA must balance the client's enthusiasm with their professional obligation to provide unbiased, evidence-based recommendations, aligned with regulatory requirements and best practices for energy auditing. The challenge lies in navigating the client's potential preconceived notions and ensuring the recommendation is technically sound, economically viable, and compliant with relevant U.S. energy efficiency and renewable energy guidelines, rather than simply fulfilling a client's initial preference. Correct approach analysis. The correct approach involves conducting a comprehensive site-specific assessment that objectively evaluates the technical feasibility, economic viability, and environmental impact of various renewable energy options, including VAUT, in the context of the client's specific needs and location. This approach aligns with the core principles of energy auditing as defined by U.S. regulatory frameworks and professional standards for CEAs. It necessitates a thorough understanding of different VAUT types, Savonius, Darius, their respective advantages and disadvantages, and their suitability for particular applications. The CEA must consider factors such as wind resource availability, site constraints, local zoning ordinances, and the client's energy consumption patterns. The recommendation should be based on data-driven analysis, comparing VAUT against other viable renewable energy technologies and conventional energy efficiency measures, ensuring compliance with relevant U.S. Department of Energy (DOE) guidelines and state-level energy program requirements that emphasize cost-effectiveness and long-term performance. Incorrect approaches analysis, recommending VAUT solely based on the client's expressed interest without a detailed site assessment, is an ethical and regulatory failure. This approach prioritizes client satisfaction over professional due diligence and objective analysis, potentially leading to an inappropriate and uneconomical investment for the client. It violates the CEA's responsibility to provide unbiased, technically sound advice as mandated by professional codes of conduct and U.S. energy auditing standards, which require a holistic evaluation of energy conservation opportunities. Proposing a specific VAUT model, e.g., a particular Darius design, without comparing it to other VAUT types or alternative renewable energy solutions, demonstrates a lack of comprehensive analysis. This approach is flawed because it assumes a priori that a specific VAUT is the optimal solution, neglecting the possibility that other VAUT designs or entirely different renewable technologies might be more suitable or cost-effective for the client's site and energy needs. This selective focus can lead to suboptimal energy performance and financial outcomes, contravening the principles of thoroughness expected in energy auditing. Focusing exclusively on the theoretical advantages of VAUT, e.g., omnidirectional wind capture, without a rigorous assessment of their practical disadvantages, e.g., lower efficiency in certain wind conditions, higher maintenance for some designs, potential noise issues, is also an unacceptable approach. This selective presentation of information misleads the client and fails to meet the CEA's obligation to provide a balanced and realistic evaluation. U.S. energy auditing standards require a complete picture, including potential drawbacks and limitations, to enable informed decision-making. Professional reasoning. Professionals should adopt a systematic, data-driven approach. This involves 1. Understanding the client's objectives and constraints. 2. Conducting a thorough site assessment to gather all relevant data, wind resource, site characteristics, energy usage. 3. Researching and evaluating all applicable renewable energy technologies, including different VAUT types and their suitability for the specific site and application, as well as other energy efficiency measures. 4. Performing a comparative analysis of technical feasibility, economic viability, including life cycle costs and payback periods, and environmental impact. 5. Presenting a clear, unbiased report detailing findings, recommendations, and the rationale behind them, ensuring compliance with all relevant U.S. federal and state energy regulations and professional ethical guidelines. Question 14. The assessment process reveals that a small-scale hydropower facility is experiencing fluctuating energy output. The Certified Energy Auditor (CE) is tasked with evaluating the system's operational efficiency and compliance with environmental regulations. Which of the following approaches would best fulfill the CEA's professional responsibilities in this scenario? Option A. Comprehensive visual inspection of the turbine and generator components to identify any physical wear or damage, without examining operational data or environmental compliance records. Option B. A thorough review of the facility's operational logs, maintenance records, and environmental monitoring data, comparing them against established operational parameters and discharge limits set by relevant U.S. federal and state regulatory bodies. Option C. An exclusive focus on optimizing turbine speed and water flow to achieve the highest possible instantaneous power generation, irrespective of downstream environmental flow requirements. Option D. A reliance on historical operational data from the past decade without verifying its alignment with current environmental discharge permits or operational guidelines. Correct answer is B. A thorough review of the facility's operational logs, maintenance records, and environmental monitoring data, comparing them against established operational parameters and discharge limits set by relevant U.S. federal and state regulatory bodies. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified energy auditor, C, by requiring them to evaluate a hydropower system's operational efficiency and compliance within a specific regulatory framework, likely the U.S. federal and state regulations governing hydropower and environmental impact. The challenge lies in balancing the technical assessment of operational parameters with the adherence to established legal and environmental standards, particularly concerning water flow and ecological impact. The CEA must demonstrate a nuanced understanding of how operational decisions affect both energy generation and regulatory compliance, necessitating careful judgment to avoid misinterpretations or oversights that could lead to noncompliance or suboptimal performance. Correct approach analysis. The correct approach involves a comprehensive review of the hydropower facility's operational logs, maintenance records, and environmental monitoring data against the established operational parameters and discharge limits set by relevant regulatory bodies, such as the Federal Energy Regulatory Commission, FERC, and state environmental protection agencies. This approach is correct because it directly addresses the core responsibilities of a CEA, assessing efficiency and compliance. By comparing actual operational data with permitted limits and best practices, the CEA can identify deviations that impact efficiency or violate regulations. This aligns with the ethical obligation to provide accurate assessments and the professional duty to ensure facilities operate within legal and environmental boundaries, as often stipulated in CEA certification standards and industry best practices that emphasize data-driven evaluation and regulatory adherence. Incorrect approach is analysis, focusing solely on maximizing turbine output without considering downstream ecological flow requirements or minimum environmental flows, represents a significant regulatory and ethical failure. This approach disregards the legal mandates designed to protect aquatic ecosystems and water quality, which are integral to hydropower licensing and operation. Such a failure could lead to penalties, operational restrictions, and damage to the facility's reputation. Prioritizing historical operational data without verifying its accuracy or comparing it against current regulatory standards is another incorrect approach. Regulations evolve, and older data may not reflect current compliance requirements. This oversight can lead to a false sense of compliance and expose the facility to legal repercussions. It demonstrates a lack of due diligence and a failure to stay current with the regulatory landscape. Relying exclusively on visual inspection of the turbine and generator components without examining operational data or environmental compliance records is insufficient. While visual inspection can identify mechanical issues, it does not provide insight into the system's adherence to operational permits, environmental regulations, or overall energy efficiency from a systemic perspective. This approach is incomplete and fails to address the broader scope of a CEA's responsibilities. Professional reasoning. Professionals in this situation should adopt a systematic, data-driven approach that integrates technical assessment with regulatory compliance. This involves 1. Understanding the specific regulatory framework governing the hydropower facility, e.g., FERC licenses, Clean Water Act, state-specific environmental regulations. 2. Gathering all relevant operational data, maintenance logs, and environmental monitoring reports. 3. Cross-referencing this data with the facility's permits, license conditions, and applicable environmental flow requirements. 4. Identifying any discrepancies or deviations and assessing their impact on energy generation, operational efficiency, and regulatory compliance. 5. Documenting findings clearly and providing recommendations that address both technical improvements and regulatory adherence. Question 15. Strategic planning requires a comprehensive evaluation of wind energy technologies for a new facility, considering the regulatory framework governing renewable energy projects in the United States, which approach best aligns with the principles of a certified energy auditor. Option A. Focus exclusively on the theoretical efficiency curves of different turbine designs, without considering the practical challenges of installation, maintenance, or regulatory approval processes. Option B. Evaluate turbine technologies based on their compatibility with site-specific wind resource assessments, projected operational performance, environmental impact considerations, and adherence to relevant U.S. federal, state, and local energy regulations. Option C. Select the turbine technology that has the lowest initial purchase price, irrespective of its long-term operational efficiency or site-specific suitability. Option D. Prioritize turbine models with the highest rated power output, assuming this directly translates to maximum energy generation and cost savings. The correct answer is D. Prioritize turbine models with the highest rated power output, assuming this directly translates to maximum energy generation and cost savings. Explanation. This scenario presents a professional challenge for a certified energy auditor, C, by requiring a comparative analysis of wind energy technologies within a specific regulatory context, without resorting to purely quantitative methods. The challenge lies in understanding the nuanced implications of different turbine designs and their alignment with the overarching goals of energy efficiency, environmental impact mitigation, and regulatory compliance, all of which are central to the CEA's role. Careful judgment is required to balance technical feasibility with the broader strategic objectives. The correct approach involves evaluating wind turbine technologies based on their suitability for the specific site conditions and their alignment with the prevailing regulatory framework, which in the U.S. context would include considerations like the Energy Policy Act of 2005, state-level renewable portfolio standards, RPS, and local zoning ordinances. This approach is correct because it directly addresses the CEA's mandate to recommend energy efficiency and renewable energy solutions that are both technically sound and legally compliant. It prioritizes a holistic assessment that considers the long-term viability and integration of the technology within the existing energy landscape and regulatory environment. An incorrect approach would be to solely focus on the theoretical maximum power output of different turbine models, without considering site-specific wind resource variability or the regulatory hurdles associated with their deployment. This fails to acknowledge that theoretical performance does not always translate to practical, compliant, or cost-effective energy generation. Another incorrect approach would be to prioritize the lowest upfront capital cost of a turbine, without a thorough assessment of its operational efficiency, maintenance requirements, or its ability to meet the energy demands of the facility, thereby neglecting the long-term economic and performance aspects crucial for energy auditing. Finally, an approach that disregards potential environmental impact assessments or community acceptance issues, even if technically feasible and compliant with basic energy regulations, would be professionally deficient as it overlooks broader sustainability and stakeholder considerations, often implicitly or explicitly embedded in energy policy and ethical auditing practices. Professionals should employ a decision-making framework that begins with a thorough understanding of the client's objectives and the specific regulatory environment. This involves identifying all relevant federal, state, and local regulations pertaining to renewable energy deployment. Subsequently, a comparative analysis of potential technologies should be conducted, evaluating not only their technical specifications, but also their environmental impact, operational costs, maintenance needs, and their ability to integrate with existing infrastructure. The final recommendation should be a well-reasoned justification that clearly articulates how the chosen technology best meets the client's needs while adhering to all applicable regulations and ethical standards. Question 16. Quality control measures reveal that a client has requested a PV system design that appears to be oversized for their current energy consumption, with a proposed array layout that may not fully optimize for the site's specific shading patterns. The client has expressed a strong preference for this specific configuration, citing a desire for future expansion and a perceived aesthetic appeal. As the certified energy auditor, how should you proceed with the performance modeling and economic analysis to ensure compliance with professional standards and ethical obligations? Option A. Redesign the PV system to an optimal size based on current energy consumption and an array layout that mitigates shading, and then perform the performance modeling and economic analysis, clearly explaining to the client why this approach is recommended for better performance and financial returns. Option B. Conduct the performance modeling and economic analysis based on the client's requested oversized system and array layout, but include detailed caveats in the report regarding potential underperformance and longer payback periods due to shading and oversizing. Option C. Adjust the performance modeling parameters and economic assumptions to artificially inflate the projected energy production and shorten the payback period, thereby justifying the client's preferred oversized system and array layout. Option D. Proceed with the performance modeling and economic analysis using the client's requested oversized system and array layout without modification, assuming the client is fully aware of the implications and accepts the projected outcomes. The correct answer is B. Conduct the performance modeling and economic analysis based on the client's requested oversized system and array layout, but include detailed caveats in the report regarding potential underperformance and longer payback periods due to shading and oversizing. Explanation. This scenario presents a professional challenge because it requires balancing the client's desire for a specific outcome with the auditor's ethical and regulatory obligations to provide an accurate and unbiased assessment. The auditor must navigate potential conflicts of interest and ensure that their recommendations are grounded in sound engineering principles and adherence to relevant standards, rather than solely on client preferences or perceived expediency. The pressure to deliver a particular result can compromise the integrity of the audit process. The correct approach involves prioritizing the integrity of the PV system design and performance modeling based on established industry standards and regulatory requirements. This means conducting a thorough analysis of the site conditions, available solar resources, and equipment specifications to determine the optimal system size, an array layout that maximizes energy production and economic viability over the system's lifespan, while also complying with all applicable building codes and utility interconnection standards. The auditor's professional duty is to provide an objective assessment, even if it deviates from the client's initial expectations. This aligns with the ethical principles of honesty, integrity, and competence expected of a certified energy auditor. An incorrect approach would be to artificially inflate the projected energy production to justify a larger, more expensive system that the client initially desired, even if the site conditions or equipment limitations do not support such performance. This violates the principle of accuracy and honesty in reporting and could lead to the client making a financially unsound investment. Another incorrect approach would be to overlook or downplay potential performance degradation factors or maintenance requirements in the economic analysis to present a more favorable return on investment. This misrepresents the true long-term economic performance of the system and fails to provide the client with a realistic understanding of their investment. Furthermore, ignoring or inadequately addressing site-specific constraints, such as shading or roof orientation, in the array layout to accommodate the client's aesthetic preferences would compromise the system's actual energy output and violate the principle of sound engineering design. Professionals should approach such situations by first clearly understanding the client's objectives and constraints. Then, they must apply their technical expertise and knowledge of regulatory frameworks to develop design and performance models that are technically sound and economically realistic. If the client's initial vision conflicts with these principles, the auditor has a responsibility to clearly communicate the technical and economic implications, offering alternative solutions that meet both performance goals and financial considerations within the bounds of ethical and regulatory compliance. Maintaining open and transparent communication throughout the process is crucial. Question 17. Risk assessment procedures indicate that a proposed wind turbine installation may have significant impacts on a protected wetland. Which of the following approaches best ensures compliance with environmental regulations and professional ethical standards for a certified energy auditor? Option A. Rely on informal discussions with local residents to gauge the wetland's perceived environmental health and resilience. Option B. Prioritize the assessment of the wind turbine's energy generation capacity and economic feasibility, assuming environmental impacts will be minimal. Option C. Conduct a comprehensive environmental impact assessment (IA) that includes detailed baseline studies of the wetland's ecology, analysis of potential impacts from the turbine, and development of specific mitigation strategies. Option D. Utilize a standard environmental compliance checklist without specific tailoring to the wetland's unique characteristics or wind turbine impacts. Correct answer is C. Conduct a comprehensive environmental impact assessment (IA) that includes detailed baseline studies of the wetland's ecology, analysis of potential impacts from the turbine, and development of specific mitigation strategies. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified energy auditor, CEA, by requiring them to assess the impact of a proposed wind turbine installation on a protected wetland. The challenge lies in balancing the potential benefits of renewable energy generation with the stringent environmental protection regulations and the need for a thorough, evidence-based impact assessment. CEAs must navigate complex environmental laws, understand ecological principles, and apply rigorous methodologies to ensure compliance and responsible development. Professional difficulty stems from the potential for significant environmental consequences, the need for interdisciplinary knowledge, and the ethical obligation to protect natural resources while supporting sustainable energy initiatives. Correct approach analysis. The correct approach involves conducting a comprehensive environmental impact assessment, IA, that specifically addresses the potential effects of the wind turbine on the wetland ecosystem. This includes detailed baseline studies of the wetland's flora, fauna, hydrology, and soil conditions. The EIA must then analyze potential impacts such as habitat fragmentation, noise pollution affecting wildlife, changes in water flow, and the risk of bird and bat collisions. Mitigation strategies must be developed and evaluated for their effectiveness in minimizing or offsetting these impacts. This approach is correct because it directly aligns with regulatory requirements for environmental protection, such as those mandated by the U.S. Environmental Protection Agency, EPA, under the National Environmental Policy Act, NEPA, for federal actions, and similar state-level environmental review processes. Ethically, it upholds the CEA's responsibility to ensure that energy projects are developed in an environmentally sound manner, prioritizing the preservation of sensitive ecosystems. Incorrect approaches analysis, focusing solely on the energy generation capacity and economic viability of the wind turbine, without a thorough environmental assessment, is an incorrect approach. This fails to comply with environmental regulations that mandate impact studies for projects affecting sensitive areas. It represents an ethical failure by prioritizing economic gain over environmental stewardship and potentially leading to irreversible ecological damage. Adopting a generic environmental checklist without specific consideration for the unique characteristics of the wetland and the potential impacts of wind turbines is also an incorrect approach. While checklists can be useful, they are insufficient for complex situations involving protected ecosystems. This approach risks overlooking critical, site-specific environmental concerns and may not meet the detailed requirements of environmental impact assessment regulations. It demonstrates a lack of due diligence and professional rigor. Relying on anecdotal evidence or opinions from local stakeholders regarding the wetland's resilience without conducting scientific studies is an incorrect approach. Environmental regulations require objective, data-driven assessments. Anecdotal information is not a substitute for scientific investigation and can lead to inaccurate conclusions and inadequate mitigation plans, violating both regulatory requirements and professional standards for evidence-based decision-making. Professional reasoning. Professionals facing similar situations should first identify all applicable regulatory frameworks, including federal, state, and local environmental laws and guidelines relevant to renewable energy projects and protected natural resources. They should then engage with relevant environmental agencies to understand specific requirements and expectations. A systematic approach to impact assessment, starting with detailed baseline data collection and progressing through impact analysis, mitigation planning, and monitoring, is crucial. This process should be iterative, allowing for adjustments based on new information or regulatory feedback. Maintaining clear documentation of all assessments, findings, and decisions is essential for accountability and compliance. Question 18. The control framework reveals that a certified energy auditor, CEA, is tasked with recommending a wind turbine for a new renewable energy project. The auditor has access to detailed wind resource assessment data for the proposed site, including average wind speeds, turbulence intensity, and wind directionality. The client has expressed a desire for a cost-effective solution that maximizes energy generation. Considering the regulatory requirements for energy audits and the professional responsibilities of a CEA, which approach to turbine selection is most appropriate? Option A. Focus on turbines with the highest rated power capacity, as this will ensure the greatest potential for energy generation, regardless of the specific wind resource characteristics of the site. Option B. Prioritize turbine models known for their high energy output in general, based on manufacturer specifications, and select the one with the lowest upfront purchase price that meets the client's budget. Option C. Select a turbine model that is currently the most popular in the market, assuming its widespread adoption indicates superior performance and reliability across various wind conditions. Option D. Conduct a detailed analysis of the wind resource data to identify turbine models whose power curves and operational characteristics are best matched to the site's specific wind speed distribution, turbulence intensity, and prevailing wind directions, while also considering site-specific constraint and regulatory compliance. Correct answer is B. Prioritize turbine models known for their high energy output in general, based on manufacturer specifications, and select the one with the lowest upfront purchase price that meets the client's budget. Explanation. Scenario analysis. This scenario presents a common challenge for energy auditors, balancing the technical requirements of a renewable energy project with the diverse needs and expectations of stakeholders. The professional challenge lies in translating complex technical data, wind resource assessment, into actionable recommendations that are both technically sound and economically viable for the client, while also considering the long-term operational implications and regulatory compliance. The auditor must navigate potential conflicts between maximizing energy generation, minimizing upfront costs, and ensuring the chosen technology aligns with the site's specific environmental and logistical constraints. Correct approach analysis. The correct approach involves a comprehensive evaluation of the wind resource data in conjunction with site-specific constraints and the client's objectives. This means analyzing the wind speed distribution, turbulence intensity, and prevailing wind direction to identify turbine types that are most efficient and reliable under those specific conditions. It also necessitates considering factors like terrain, existing infrastructure, noise regulations, environmental impact assessments, and grid connection requirements. The regulatory framework for energy auditing, particularly concerning renewable energy projects, emphasizes due diligence, accuracy, and providing recommendations that are technically feasible and economically justifiable. The CEA's role is to provide an objective assessment that supports informed decision-making, aligning with ethical obligations to act in the client's best interest and adhere to professional standards. Incorrect approach is analysis. Selecting a turbine solely based on the highest average wind speed without considering other resource characteristics like turbulence or diurnal patterns is a failure to conduct a thorough site-specific analysis. This can lead to suboptimal performance, premature wear, and increased maintenance costs, violating the principle of providing technically sound advice. Choosing a turbine based primarily on the lowest initial capital cost, without a comprehensive assessment of its long-term operational efficiency, reliability, and suitability for the specific wind regime, represents a failure to consider the total cost of ownership and potential life cycle risks. This can lead to a project that is not economically viable in the long run, potentially breaching the duty to provide financially responsible recommendations. Opting for a turbine model that is widely used in other regions but has not been adequately assessed for its performance in the specific local wind conditions or against local environmental regulations demonstrates a lack of due diligence. This can result in noncompliance with local permitting requirements or poor performance, failing to meet the standard of care expected of a certified energy auditor. Professional reasoning. Energy auditors must adopt a systematic, data-driven, and client-centric approach. This involves 1. Thoroughly understanding the client's objectives and constraints. 2. Conducting a detailed analysis of the available wind resource data, including not just average speeds, but also variability, turbulence, and directionality. 3. Integrating site-specific factors such as topography, environmental sensitivities, noise limits, and infrastructure availability into the evaluation. 4. Researching and evaluating turbine technologies that are demonstrably suitable for the identified wind resource and site conditions, considering factors beyond just initial cost, such as efficiency curves, reliability data, and maintenance requirements. 5. Ensuring all recommendations comply with relevant local, state, and federal regulations pertaining to renewable energy installations and environmental protection. 6. Presenting a clear, well-justified recommendation that balances technical performance, economic viability, and regulatory compliance. Question 19. Process analysis reveals that a rural community is seeking to enhance its energy independence and reduce its carbon footprint through the integration of small hydropower systems. The available water resource is a moderately flowing river with a consistent, but not significant, natural head. The community has expressed a desire for a system that minimizes disruption to the local ecosystem and existing land use, which approach best aligns with these objectives and the principles of responsible energy auditing. Option A. Focus solely on the lowest upfront capital cost of a pico-hydro system, without considering its limited power output or its suitability for the community's overall energy requirements. Option B. Advocate for the construction of a small impoundment dam to maximize energy generation potential, regardless of potential ecological disruption or the need for extensive land acquisition. Option C. Prioritize a run-of-river hydropower system, carefully assessing flow variability and potential downstream impacts, while ensuring compliance with all environmental permits and grid interconnection standards. Option D. Recommend a micro-hydro system, assuming it will be sufficient for the community's needs without a detailed analysis of the river's actual power generation capacity or the community's energy demand. Correct answer is C. Prioritize a run-of-river hydropower system, carefully assessing flow variability and potential downstream impacts, while ensuring compliance with all environmental permits and grid interconnection standards. Explanation: this scenario presents a professional challenge for a certified energy auditor, C, by requiring them to evaluate the optimal approach for integrating small hydropower systems into an existing energy infrastructure. The challenge lies in balancing technical feasibility, environmental impact, regulatory compliance, and economic viability, particularly when considering different types of small hydro systems. Careful judgment is required to select the most appropriate system based on site-specific conditions and overarching energy policy objectives, without resorting to a one-size-fits-all solution. The correct approach involves a comprehensive site assessment that considers the specific characteristics of the water resource, flow rate, head, environmental sensitivities, local grid interconnection requirements, and relevant energy policies. This approach prioritizes a thorough understanding of the site's potential and limitations before selecting a hydropower system type. For instance, a run-of-river system might be favored in areas with consistent flow and minimal environmental impact, while an impoundment system might be considered where storage is necessary, provided environmental concerns can be adequately mitigated. Microhydro and picohydro systems are typically suited for smaller-scale applications or off-grid scenarios. Regulatory justification stems from the need to comply with all applicable federal, state, and local regulations pertaining to hydropower development, environmental protection, and grid interconnection standards. Ethical considerations demand a commitment to sustainable energy practices and minimizing negative environmental externalities. An incorrect approach would be to prematurely select a specific hydropower system type based on a superficial understanding of the site or a preference for a particular technology without a detailed assessment. For example, advocating for an impoundment system solely because it offers greater energy storage potential, without conducting a thorough environmental impact assessment or considering less intrusive alternatives like run-of-river, would be a regulatory and ethical failure. This ignores potential impacts on aquatic ecosystems, downstream water users, and land use. Similarly, recommending a micro-hydro system for a large industrial facility without verifying its capacity to meet demand would be technically unsound and a failure to adhere to professional due diligence. Another incorrect approach would be to overlook the specific grid interconnection standards and permitting requirements for small hydropower projects, leading to non-compliance and project delays. This demonstrates a lack of understanding of the regulatory framework governing energy infrastructure development. Professionals should employ a decision-making framework that begins with a detailed site-specific analysis, followed by an evaluation of various small hydropower system types against established criteria including technical suitability, environmental impact, regulatory compliance, and economic feasibility. This iterative process ensures that the chosen solution is not only technically sound, but also environmentally responsible and legally compliant, aligning with the CEA's professional obligations. Question 20. The control framework reveals that a certified energy auditor, C, is tasked with evaluating the potential for flat-plate solar thermal collectors for a mixed-use residential and commercial building. The auditor has access to manufacturer datasheets detailing collector efficiency under standard test conditions, STC, and has conducted a site visit to assess potential shading and available roof space, which approach best ensures the accuracy and applicability of the auditor's recommendations for domestic hot water and space heating applications. Option A. Focus on the collector's construction materials and warranty, as these are the primary indicators of long-term performance and reliability. Option B. Prioritize the STC efficiency ratings from datasheets and assume these will be achieved consistently across all applications and seasons. Option C. Integrate STC data with site-specific environmental factors, insulation, ambient temperature, shading, and consider the distinct thermal load profiles of domestic hot water and space heating to estimate realistic energy delivery. Option D. Recommend the highest efficiency collector based solely on its peak performance rating, assuming it will provide the greatest overall energy savings regardless of installation specifics. The correct answer is B. Prioritize the STC efficiency ratings from datasheets and assume these will be achieved consistently across all applications and seasons. Explanation. Scenario analysis. This scenario is professionally challenging because it requires an energy auditor to balance the theoretical performance characteristics of flat plate collectors with the practical realities of their installation and application in a specific climate. Misinterpreting performance data or overlooking site-specific factors can lead to inaccurate energy savings projections, potentially resulting in suboptimal system design, client dissatisfaction, and non-compliance with energy efficiency standards or building codes. The auditor must demonstrate a nuanced understanding of how design choices and environmental conditions impact real-world output, moving beyond simple datasheet values. Correct approach analysis. The correct approach involves a comprehensive evaluation of flat plate collector performance that considers both design specifications and operational context. This includes understanding how factors like collector tilt angle, azimuth, shading, ambient temperature, and fluid flow rate influence the actual energy delivered for domestic hot water and space heating. Regulatory frameworks for energy auditing, such as those potentially referenced by the Certified Energy Auditor (C) certification, emphasize the need for accurate, site-specific assessments. This approach aligns with the ethical obligation to provide reliable and actionable recommendations that lead to demonstrable energy savings and compliance with relevant building codes and performance standards. The CEA certification implies a commitment to adhering to established best practices and guidelines that prioritize realistic performance evaluation. Incorrect approaches analysis. An approach that solely relies on manufacturers' rated efficiency without considering site-specific environmental conditions and installation details is professionally flawed. This fails to account for real-world performance degradation due to factors like suboptimal tilt or azimuth, or excessive heat loss in colder climates, leading to inflated savings estimates. This violates the principle of providing accurate assessments and could result in non-compliance with performance benchmarks. Another incorrect approach would be to focus exclusively on the collector's construction materials and design features without correlating them to actual energy output under typical operating conditions. While understanding construction is important for durability and maintenance, it does not directly translate to performance metrics required for energy auditing. This overlooks the core requirement of quantifying energy savings and efficiency improvements. Finally, an approach that prioritizes a single application, e.g., only domestic hot water, and ignores the potential for dual use or the specific demands of space heating in a given climate is incomplete. Different applications have varying temperature requirements and usage patterns, which significantly affect the optimal design and performance of flat plate collectors. This narrow focus can lead to recommendations that are not fully optimized for the building's overall energy needs. Professional reasoning. Professionals in energy auditing must adopt a systematic and holistic approach. This involves 1. Understanding the specific regulatory and certification requirements, e.g., CEA guidelines that dictate the scope and accuracy of the audit. 2. Thoroughly analyzing the building's energy consumption patterns and identifying opportunities for solar thermal integration. 3. Evaluating the performance characteristics of potential solar thermal technologies, such as flat plate collectors, by considering both manufacturer data and site-specific environmental factors. 4. Assessing the suitability of different collector designs and configurations for the intended applications, domestic hot water, space heating, and climate. 5. quantifying projected energy savings and economic viability with a high degree of accuracy, ensuring recommendations are practical and achievable. 6. Documenting all assumptions, methodologies, and findings clearly and transparently.